All right, so we are now in chapter 9. We're going to be doing nucleophilic substitution and elimination reactions. This will be the first part of that. We'll actually have a two-part series here. All right. And so we're going to have 4 reactions, and these all compete whenever we do them. You may have noticed that the conditions these happen under are pretty similar, right? We typically have a base or a nucleophile, right? All the things we talked about as being a good base and a good nucleophile, basically all of them are true of all that stuff, right? See, a base can accept a proton, meaning it has a pair of electrons, doesn't it? A nucleophile has a pair of electrons, doesn't it? And so they're really similar at this point, right? And then we have a leaving group on all these, and wow. They've really overlapped, right? And so these reactions typically compete with each other. And you need to actually understand how you can differentiate these. Now, there's actually a fun little factoid. When I was, so last year, August, July actually, beginning of July, I had been laid off from Bethel University, and I actually was applying for jobs, and I got offered like 3 or 4 jobs all at the same time. I ended up taking this one. But one of the things that I got asked the most often whenever they wanted me to teach organic chemistry is questions involving like this competition and which one would win. And apparently I was like the only one that actually answered correctly for one of them. Because when I answered, I don't know if the person knew the video camera was on, they like had a tablet of paper over the questions, and they were like, yes. So apparently there's a lot of professors that can't teach you this, right? I don't know what to say about that one, but it's not that hard. Okay, so we're going to learn a little bit today about how to differentiate which one is going to win that. Okay, now notice that a lot of these cases you will actually have like 2 of these that'll be a possibility, and you may actually end up with a mixture in some very somewhat unique cases. Okay, but the likelihood of you actually ending up with a mixture is not super high. All right. Now, the reactions we need to remember here are SN2, SN1, E2, and E1. You'll remember that the E1 and SN1 actually share the first step, right? So they have a lot in common already. Okay? Now, all of these are going to involve a substrate. They'll contain a leaving group. Any species that can act as a nucleophile also will have the potential to act as a base, and that is vice versa. That's true both ways. To acknowledge this ability to act as either type of species, we're going to oftentimes refer to as a nucleophile or a base, more generally as an attacking species. And you may have noticed that I had already used that terminology many times in front of you all, where I had referred to them as attacking species, and you all pretty much knew what I was talking about right off the bat, right? They're attacking with those electrons, aren't they? Okay? We have a little arrow going in, just like we would like a sport, right? You're the attacker, go up the main field. Yep. And yeah. Looks just like a basketball diagram, doesn't it? You here, you here. Okay. And so when acting as a nucleophile, an attacking species is going to use a lone pair to form a bond to an electron-poor non-hydrogen atom. This is the difference between these. When acting as a base, the attacking species forms a bond to a hydrogen atom because it's going to accept a proton, right? NH+. And so right here, we can actually see the mechanisms for the SN2 and SN1 reactions. So in the SN2 reactions, we have the attacker attacking, and then the leaving group is going to leave as part of that. Okay? It happens all in one step. In an SN1 reaction, on the other hand, the leaving group leaves first. We generate the carbocation, and then the attacker is going to attack that. Okay? And so that's the different important differentiation. Okay, everything that results from that is going to result in these reactions acting a little bit differently. You can already actually kind of figure this out, right? So if we have to attack into this, Well, this is going to be harder to attack, isn't it? Because you got to force that leaving group to leave, don't you? Okay? And so this means our attacker has to be a better attacker, right? Just like if you're watching sports and you have a goalie and it's guarding the goal, right? Then your attacker has to be a better attacker to score a point. Okay? If you don't have any goalie there because somebody like ran into him or they took the goalie out to try to do a full attack or whatever, then you don't need a good attacker, do you? They can be a pretty bad attacker. They just have to have the ball. Okay? If they can keep the ball, then they're good enough. All right. So, did football analogy work well? Everybody understands football to some degree. Okay. Well, soccer, excuse me. God, obviously I've been around too many Europeans. No, I need to cut the number of Europeans and Canadians also referred to as football. No soccer. Then I can keep 50-50 Canadians in my life. Got one in every two. You really are. You've been using purely units a lot. Yeah. Okay, so this is the E2 and E1 reaction here. And again, we're going to have for the E2 reaction, attacker has to attack. In this case, it's going to be attacking a hydrogen, right? And so this is going to be acting as a base. Notice this one right here was acting as a nucleophile. Okay? So this one acts as a base. So the attacker attacks. It needs to take that hydrogen off. It's going to leave the electrons behind as that double bond, and that's going to push the leaving group off. Okay? Notice again, our leaving group doesn't have to be amazing for this. If we have a strong enough attacker, it can attack through it, right? Okay. Now, over here where we have the E1, well, our leaving group leaves first. And so our leaving group has to be really, really good leaving group, right? It has to leave well. Okay? And then our next step is going to be the base taking the hydrogen off. But notice that because this has a positive charge, this is a lot better of an acid. Okay? If you remember our cardinal charge was the C, right? The first one, the big one. And so it being charged like that makes it a much, much better acid, doesn't it? Okay? And that means our base here doesn't have to be a very good base. This just has to be a strong enough base to accept a fairly acidic proton right there. Okay? Okay. So let's talk about the rate determining steps for these, because the rate determining step is going to be half of that equation that determines what's going to happen in any given reaction. We have two parts of will a reaction happen, right? So we have the is it spontaneous, right? So why are you not lighting on fire right now? I mean, we're all flammable. Not spontaneous, right? Okay. So it's not spontaneous for your blood to light on fire. It's not spontaneous for your moisturized skin to light on fire. Your hair has a little bit of water in it. It's not spontaneous. Okay? And so it's not a spontaneous process. Now, the Grand Canyon forming, that is a spontaneous process. We've had water going through this area, right? So eventually, if water keeps flowing through this area, we would expect a Grand Canyon to form. Why are we not standing in a Grand Canyon right now? It takes a long time. There's also the rate, right? So why is your car not exploding right now? No, it'll still be spontaneous. We won't form an equilibrium, at least not right now. So what's happening is you just are so slow that it would take like 1 million years to form the Grand Canyon. Or in the case of your car not exploding right now, it's happening very, very slowly. That's oxidizing the gasoline. And so it'll oxidize it over the course of like 6 months. And that's why if you left the same tank of gas in there, you won't be able to start it after about 6 months to a year-ish. And you'd probably have to clean out your engine if you left it more than a year. Okay? It depends on, how much oxygen was able to exchange and stuff. But if you got lucky, you might be able to go a couple of years. But again, that's just pure rate. That will the gasoline is spontaneously oxidizing. It's just happening so slow, right? And so determining what would happen is always going to be a game where you play that between the rate and what is the most energetically favorable product, right? If you got the most energetically favorable product, but it's super slow, well, then by the time it tries to do its reaction, everything else is going to be gone, right? And so you don't do the reaction, okay? And if you have things that are within the same about speed, but you have one that's not spontaneous, well, the non-spontaneous one's not going to happen, is it? Okay? Okay. And so again, this is the mechanism for the general SN2 reaction. Again, we have our nucleophile. It's going to attack, right, our substrate. And this is going to cause our leaving group to leave. We have the SN1 reaction here. The leaving group leaves. And this is going to give us the carbocation on our substrate. The nucleophile then attacks that carbocation in this second step. Okay? When we look at these steps, again, the SN2 reaction, that only has one step, and so that is the slow step. The SN1 reaction, this first leaving group part, that is the slow step. And so these determine which is going to happen faster, don't they? Okay? Will this step happen faster, or will this step happen faster? Okay? So what actually determines how fast these steps happen? Well, this one is a combination of attacker attacking and leaving group leaving, right? Remember how we did those rate laws a bit ago? Well, the rate law told us that, didn't it? It told us the concentration of this and the concentration of this gave us that rate. Okay? The rate law here told us the concentration is only dependent on the leaving group leaving here. And so in the case of an SN1 reaction, the rate is totally dependent on how good that leaving group is at leaving. Okay? That's it. It doesn't actually matter how good our nucleophile is at attacking. By the time we worry about our nucleophile, we're already in the fast step, aren't we? It just doesn't matter. Kind of like anybody that can dribble a ball can score on a goal with no goalie. As long as you can move the ball over there. Guess you don't even have to dribble. You could just do like short kicks. It would work. Now, this is the mechanism for your E2. Again, this is the generalized one that you don't have to worry about what species is what, etc. We have the base. It's going to give its electrons into a bond with the hydrogen, the H+, right? That's going to leave its electrons in the double bond, which causes the leaving group to leave. And so again, in the E2, that 2 tells us this reaction rate is dependent, is this first step, the only step. And the reaction rate is dependent on the concentration of the base and the concentration of our substrate, right? And so both of these factors count. So if you have a better base, you can make up for some of that substrate leaving group not being as good. Okay? So this one right here, this is the E1 reaction. Again, our slow step is the first step, isn't it? And that's the leaving group leaves. And that's the only one that's in the rate law. It's the concentration of our substrate with the leaving group. And so again, when we're looking at this E1 again, it's just going to purely depend on how fast does that leaving group leave. Okay? This base doesn't have to be a particularly great base, right? All that really matters in the case of this base is going to be that, well, can it act as a base and take that hydrogen away? And that's the main purpose of the base. Don't have to have a great base. Okay. I like doing that where I take you through the chain of logic, by the way. Do you guys have any understanding of why I'm making you do that? It's not just to torture you and hear my voice. So that's how you learn to actually think logically, is you see inside of the minds of people that think logically, and then that pure chaos rubs off on you. That's how you learn deductive reasoning logic, right? Okay, I'm also using a Socratic method. That's why I'm actually questioning you guys, making you guys try to think of the questions. Though I can't do it individually because the class side doesn't allow that. Okay, this right here is actually relative SN2 reaction rates. So right here we have nucleophiles, different nucleophiles doing this reaction. And what do you kind of notice as we get along these nucleophiles? Yeah, our reaction rate's increasing. So notice that when we have Lone pairs, we can do some reaction, right? Not very fast, but we can do reactions, okay? And then we get up here and we start seeing faster reactions. And again, these are going to be things that have lone pairs and negative charges, right? And then we start getting up here even more, and we start seeing things where we have like very concentrated negative charges that can move out and sort of attack things, right? That have a lot of deformability, okay? Especially on things that do not normally carry charge well, like a carbon, right? Okay. And so this is going to be the strength of the nucleophile. This is going to promote a faster SN2 reaction, and that's typically called nucleophilic strength or strength of your nucleophile. Okay? You'll notice that the Hammond postulate, so for two elementary steps that are the same type, the one with the more negative value of delta G naught reaction tends to have the smaller energy barrier and tends to be faster. And so what we see right here is right here we would actually have this free energy going down. This is a negative value. And notice the transition energy is going to be much closer to reactants, right? And so this reaction would also be faster, wouldn't it? Okay? Because your transition energy is much lower. Faster to go over the small barrier here. Now, if you, on the other hand, have a higher energy product, what you're going to see here is that your transition energy ends up being much larger usually. Okay. Again, this postulate is an overall observation. That's an overall pattern. Okay. It is not like 100% every single time. There is no possibility of it. Okay. You can contrive circumstances, but overall, this holds true for the vast majority of cases. Okay, it's actually a very good postulate. It holds true almost all. Okay, and so if we apply this to an SN2 reaction, what we can see here is that we have here the same sort of product. Our product has been evened off here, so we've been normalized. And then we have our reactants right here. Now, notice that the bromide here is more stable. And so this is going to give you a lower energy reactant. Our delta G is going to be smaller. We're going to have less down. See that? Smaller magnitude. This one here is going to have a larger magnitude delta G. Okay? Okay, so if we actually look at this energy difference between the reactants and the transition state, which one's going to be the faster reaction? Chloride. Yeah, the chloride is going to be quite a bit faster, right? So not as only is it more spontaneous, it will also be the faster reaction as well. Okay, so let's talk about the rates of the SN1 reaction. Now, again, when we look at the SN1 reaction, because the slow step has nothing to do with the nucleophile, right? At all. So that transition state has nothing to do with the nucleophile either, does it? And so what we end up getting is that the nucleophile just doesn't matter. It doesn't matter which nucleophile we have. We're going to get almost the same reaction rates for these. And so we'll get about the same amount of rate of reaction for almost any nucleophile, as long as it's a nucleophile. Okay? As long as it's an SN1 mechanism. Okay. Notice again, these would have been different strengths of nucleophiles. This one's quite a bit stronger. The N3- is quite a bit stronger right here. It's 50 times stronger than this one. So this would have been a much, much better nucleophile. And yet we get essentially the same rate for these reactions because they're the SN1 reaction. Now, the nucleophile strength in the SN1-2 versus the SN1. If we have a strong nucleophile, this is going to tend to favor your SN2 reaction because you can think of it as a strong attacker, right? It doesn't need to wait for the leaving group to leave, right? It can just attack. Okay? This would be like a, what's the best attacker in soccer right now? Or football? Anybody a big fan? Okay, this would be like a Michael Jordan in basketball. Michael Jordan didn't need to wait for people to not be in front of the hoop, right? Okay, or LeBron James. LeBron doesn't need to wait for people to evacuate. 2-3 people in the way, whatever. Still scores, right? And so it doesn't need to wait for the attack, right? It just can attack, and it's fast enough that it's going to overwhelm that leaving group leaving on its own. Okay? And so this would be your strong nucleophiles right here. These would be strong nucleophiles. Okay? Notice that these right here are actually the alkanes with the anions. Okay? Those would be your carbanions. These right here would be like the hydroxide right here. And then we come down and it's like the sulfides. And then this is your halides right here. Okay. So notice that these ones right here are going to be your weak nucleophiles. Now in the case of a weak nucleophile, this is going to be a poor attacker. Okay. It is probably not going to beat out the leaving group leaving. And so your weak nucleophiles are going to tend to favor your SN1 reactions because the leaving group leaving is typically going to be the faster thing. These would be so slow of reactions that the leaving group leaving on its own is usually the faster way. Okay. Now, notice that strong nucleophiles tend to have a -1 charge to them. That's actually a lot of what makes them a strong nucleophile, is because they have -1 charge. They have a lot of electron density, right? And so that electron density can reach in and cause things to happen, right? I.e., it can reach in, make a bond, and then displace that leaving group, right? Okay. Now, the weak nucleophiles tend to be uncharged. Again, this is a generalized rule. Can you find weak nucleophiles that would have a charge? Yes. It would be very, very spread out. Okay? Can you find a strong nucleophile that could possibly be without a charge? Yeah, probably. It would have to have a very weird concentration of charge, though. Okay? But again, I always want to stress that because, well, I actually do want you, if you invent some cool thing that violates the rules, you should definitely send me an article. Haha, Dr. Clausen, I violated your rules. Take that. Okay? I'd actually really get a kick out of it, obviously. Just like I am happy if you guys disagree with me, you just got to back your statements up, right? That we're in science. We're not in opinion land. So, got to back it up. Now, carbanions, these are going to be carbons with a negative charge, like the name indicates pretty clearly, right? So carbon with a negative charge. And carbanions are going to possess a lone pair of electrons. These can be used to form a bond. And so these are going to be very strong nucleophiles because carbon's not very electronegative. It's going to have a very, very localized condensed charge it can attack with. Okay? Very high energy group. Simplest way to generate carbon nucleophiles is actually to deprotonate an on-charged system. So this is a pretty common way to make a nucleophile out of a carbon system. Alkanes have a pKa value around 50. So they're such weak acids that deprotonation is typically unfeasible for an alkane. The pKa values for alkynes is about 25, approximately-ish. And so that's much lower than your alkanes. And so they're the much more common version of these. For example, you can use a hydride. This is hydride right here. Hydrogen with negative charge and a lone pair. This right here is more basic. This one's more acidic. And so we would actually deprotonate this, creating our alkynide anion. Is everybody okay with that language? Alkyne, right? Ide because negative charge, lone pair. And then anion because negative charge, lone pair. We're actually reinforcing. Okay, so this right here would be a very strong nucleophile. And so it can attack very successfully in an SN2. And then we could join, make a new single bond. And then make a new spot on this where we've introduced an alkyne, right? Nice little triple bond. All single bonds. Yeah. It's very difficult to take a hydrogen off that. There's very few things that are more basic than that. That would be strong enough bases to take a hydrogen off of that. Is it? You can. It's just really, really hard to do. You would have such a strong base that it would have to generate it in situ. And it'd be very hard to target too. Nobody does it. It's actually easier if you're going to try to add an alkane to something. We'll talk about it more in synthetic. Is you'd actually want to add a double or triple bond like we did here, and then you can hydrogenate off the double or triple bond and get rid of it. That's an easier way of doing that. But yeah, you cannot strip an alkane of its hydrogen without extreme circumstances. Double bonds are easier to strip, by the way. So again, the double bond was more acidic, had a more acidic hydrogen. Okay, and so the rates of your E2 reactions is generally going to increase as the strength of the base increases. And so your E2 reaction is going to be directly proportional to the base. Notice this hydroxide here. It's a strong nucleophile, but wasn't an amazing nucleophile, was it? It was like mid of the pack, okay? But over here, all of a sudden, we're looking at relative E2 rates. These are relative rates, by the way. This is why it's a 1 versus 353. That this is almost top of the pack, right? So hydroxide is a very strong base. It's actually the dividing line of strong bases. Anything stronger than hydroxide is considered a strong base. Okay. On the other hand, it's kind of a middle of the pack strong electrophile. Okay, or nucleophile, excuse me. This is your pKa's, by the way, of your bases. This is actually what determines whether that will be able to strip the hydrogen off. So notice, for example, hydroxide actually cannot take this hydrogen here in any significant quantities. We would not deprotonate that with hydroxide. That's why you have a hydride here instead. That's an even stronger base. Okay. And so, again, the reaction rates are going to vary based on your choices you make here. And so we have this carboxylate right here. And so this is a base, right? We have here, over here, we have the hydroxide, which is a much stronger base. This is a weak base, strong base. And so, which would you expect to be faster? Stronger base. Yeah. This is going to be much faster reaction, isn't it? For that E2 reaction. Okay. And so that actually is the what we're looking at here. Again, we've normalized the products to make it easier to compare. And we have right here the reactants, the stronger base, higher energy. And so we have a larger delta G. We also have a smaller activation energy, don't we? Okay, which is going to make that reaction much faster. And over here's the weak base right there. Okay, so let's talk about the base strength and the E2 versus the E1 reactions. So your rate of your E1 reaction is essentially, again, independent of your strength of your base. Once you generate a carbocation, it doesn't really matter how strong your base is, you're just so high energy already. That activation energy just can't get much higher after you made that carbocation. Okay? And so your strength of your base doesn't really matter much. Your E2 rate, though, is going to be highly sensitive to your base strength. You may not do it at any significant rate unless you're a strong base. And if it's not strong enough, like we talked about before, you may not do it at any significant amount. Okay? Because it is highly dependent on that base being strong enough to take that hydrogen off. Okay? Now, again, that's because our rate law, right? That we have the two concentrations that play in here. That tells us that this base strength actually matters. Okay, these right here are the weak versus the strong bases. You already kind of knew these from general chemistry and the work we've done with Cardinal and such. That's one of the reasons we were doing that, is we needed all that for this now. You may have noticed that every single thing we've built up all contributes in your understanding of the next material. It makes it easier to understand, right? Yeah. You'll notice this in next semester a lot. Like, we have 3 chapters next semester that will actually be fully unique material. And then everything else you're going to go, oh, this is just a result of what I already know. Okay? That's why next semester is usually easier. Okay. And so again, here we have our weak bases. Notice these are not even normally called bases. Yeah. They are technically bases, but they're the conjugate base of a strong acid, right? Right here, again, we have more of the weak bases, and then these are the strong bases. Notice, again, hydroxide is the cutoff for strong bases. It's the first strong base. Everything after that is a stronger base than hydroxide. Okay. Right. And so strong bases are going to tend to favor your E2 reactions. They get strong enough where they can really start attacking faster than the leaving group can leave. Okay. The weak bases, on the other hand, are going to be substantially weaker than hydroxide and tend to favor your E1 reactions because their rates would be so slow that your leaving group leaving is usually the faster way to go. Okay. Now, the phenoxide anion, which is this one right here, this is going to be is it a strong base or a weak base? Will it tend to favor the E1 or E2 reaction? I know I'm making you use that table I just gave you. Did you understand what I just told you? I'm going to give you till 37, and then we'll move on. It is a really good idea to argue this unless you're fully sure, because explaining it to another person is actually your best way to learn. And being explained to you by your peers is actually more effective than the professor explaining. That's in every study that's ever been done, which is really weird. Yes. Everybody have their answer in their head? Fantastic. Okay. So the pKa values of this are, 10 versus 14. So it's a significantly stronger acid than H2O. This would mean that the phenoxide is actually a weaker base than the OH minus, right? And so being significantly weaker than OH minus, it would be classified as a weak base. This is actually one of the relatively rare cases where any alkane oxide is actually a weaker base than OH minus. The reason for it is actually because of the phenyl group right here, phenoxide. So the E1 reactions will be favored by weak bases. Your E2 reaction would be favored by a strong base. And so because this is a weak base right here, this is going to favor the E1. Okay. And so you may have noticed this if you looked up your pKa value. The other part of it, you may have noticed there's a pattern where there's some of these oxides that if you have resonance structures to them, then that can give you a weaker base than you'd otherwise think. Now, let's go ahead and start talking about size. So this is the other place where it's going to matter a lot, right? So notice I was talking about number of defenders when I was talking about basketball and soccer/football, okay? And so if you have a bunch of defenders around the goal, then even if you have a strong attacker, are they going to be successful all the time? No, if you have too many defenders, even they can't get through, right? So size actually matters a lot for these things. So that steric hindrance, this is going to be caused by things like methyl groups. It can prevent the oxygen atom from actually being able to get in and attack. And thus it can actually slow down the reaction. So strong bulky bases tend to favor your E2 reactions over your SN2 reactions. This is because the strong bulky bases are going to have a very difficult time accessing that carbon. Remember, it has to access this little orbital here, doesn't it? Remember that? That's that antibonding orbital right there, right? And so if it can't get to it, well, it can't attack very well, can it? Okay. On the other hand, when you're talking about an E2 reaction, a strong bulky base, well, this can access the hydrogen much easier because it has that additional space where it's poking out with hydrogen, isn't it? Okay. So it's quite a bit more accessible. So you can actually use the bulkiness of your base to prevent things like an S2 reaction. And make it go to an E2 reaction instead. Okay. And so that's your strong bases, but they're bulky. These are some examples of strong bulky bases. There are many strong bulky bases. You can custom make these things, but these are widely available in the market. Okay. And so tert butoxide. This one's probably the most common one, by the way, which is LDA. This is the one I've seen used the most often, but it's a very strong base. Okay. So again, these are right here are going to be the summary of your reactions empirical rate laws that we had mentioned a few times now. Anybody have any questions about that or had any misunderstandings at this point about that? Okay. If you still do have any misunderstandings, don't understand something about it, please do let me know. Attacker. Because we don't really care whether it's a nucleophile or base right now. We're just trying to point out similarity. Okay. So again, when you're talking about the two reactions, the SN2, E2 reactions, it's going to be both the attacker strength, right? And then your leaving group. Okay, those both have to happen. The concentrations of those both matter. Okay. When we're talking about the SN1 reactions, then it's just the leaving group. That's all that matters. Okay. So the only thing that matters here is the concentration of your substrate leaving group and how good of a leaving group that is. Okay. Now, a high concentration of a strong nucleophile base will promote a fast SN2 or E2 reactions. This is going to favor your SN2 or E2 reactions over your SN1 or E1 reactions. If we have low concentrations, on the other hand, what happens to our rates? They go down, don't they? Yeah. So if we have a low concentration of attacker, we can actually flip that to favor the other. So if we keep that concentration really low, we can start getting it favoring the SN2 or E2 reactions. This does mean an interesting factoid. Let's say that you added equivalent amounts of two reactants. Well, at the beginning, you could be doing an SN2 or E2, right? And then towards the end, you could actually run out of reactant, couldn't you? If you run out of reactant, it's low concentration, you'll start getting a different product. So if you're not careful with the amounts you add, you can actually get the different products. It's one of the reasons why I'm always making you measure out reactants, even though it's excess. You do have to measure them out to some degree. You can't just sprinkle this, dash that. Because you could actually change the type of reaction you're doing, right? Okay, so a weak nucleophile or base is going to tend to favor an SN1 or E1 reaction over an SN2 or E2 reaction. This is going to be regardless of concentration. The concentration just can't make up for the fact that it's a weak acid or base. Okay. Strong acid or base, though, strong base or strong nucleophile, low concentrations will favor the SN1 or E1 reaction. Now, we may assume that a higher concentration of attack species is present unless it has been deliberately made dilute. So how you would see this is that would typically be noted, dilute, and then you'd have your attacking species. Okay? And we're particularly noting we have added a dilute concentration of this. Okay? Otherwise, you're always going to assume that there's plenty of the reactant. We're not going to have to worry about being low concentration. Okay? So, which reaction or reactions are favored by A high concentration of HS minus, and B, a low concentration of HS minus? So, which of these reactions or reaction would be favored by those? So, go ahead and commit somewhere. I'd recommend writing it down so you can go, ooh, this is star, need a little extra help. Or maybe you get to go, ooh, I got it right. And I understood this perfectly. Give you a minute or so. HS minus. Mm-hmm. Yes, the sulfide. So there's kind of two major questions in here, right? Is it a better base or a nucleophile? Is it a strong base, strong nucleophile? And we talk about the concentration. Go forward. So the first thing we have to do is classify HS minus. So this is going to be a strong nucleophile. It has a -1 charge. So strong nucleophile. Now HS minus would actually be a weak base in this case. And so it's weaker than OH minus. And this one actually, interestingly enough, is pretty easy to identify from cardinal because this is less electronegative than this, right? This is a larger group here. And so if you look up the pKa's, though, we would see 7.2 versus 14, which means that's a lot better of an acid, right, than the oxygen is. Now, because the HS minus is going to be a significantly weaker base, that S can accommodate a negative charge better than the oxygen. So when we're looking at this weak base, that means the E2 is probably not in the cards, right? We're not going to see a lot of that E2. Okay, so the ones we have to sort of consider now are going to be the SN2, the SN1, and E1. So again, we have a strong nucleophile. If we have it at high concentration, then what's going to be the favored reaction? Yeah, the SN2. Yeah, that's going to be your fastest reaction, and so that would be the favored reaction. Okay? Okay, what if we have it at low concentration? It'll favor the SN1 over the SN2. Now, again, it would favor the E1 over the E2, regardless of concentration. In this case, it is a better nucleophile than it is a base. And so you would expect it to do more of the SN1 rather than necessarily the E1. Okay? But you may actually get some mixture of product here at low concentration. At high concentration, it's the SN2. Because the SN2 will be heavily favored at that rate. Okay? But yeah, these ones would have very similar behaviors in terms of that slow step. You'd have to have it based on the energy difference if we're going to look at that. In this case, we don't actually have to compare those yet, though, because this question just asks us to identify. So factor 3, this is going to be your leaving group ability. So this is the alkyl tosylate right here, typically done as ROTS right here for tosylate. And this is going to have an SN2 reaction that's 300 times faster than a comparable alkyl chloride, because this is actually an incredibly good leaving group. Okay? That's because it's very, very stable with that negative charge. You may notice there's all these delocalized electrons that I can do resonance structures with. So it shares that negative charge among the entire structure. So again, this is a leaving group ability of these tosylate anions is going to be 300 times greater in an SN2 reaction than a chloride anion. And so your leaving group of this in an SN1 reaction is going to be 10,000 times greater than that of the chloride. Because again, we actually wait until the leaving group leaves, and in the SN1 reaction, right? We don't have the attacker attacking and have to deal with that. Okay. And so this is actually the how good of a leaving group do you have? Okay. And you may notice here, these were like the hydroxides and alkoxides and things like those. Amides. These right here are the halogens. Notice fluoride is a terrible leaving group. The hydroxide, terrible leaving group, right? And that's why we were like, let's avoid that at all costs. The terrible leaving group. The chloride bromide, chloride's actually starting to get to be a leaving group that you'd actually see leave in these reactions, right? And so bromide here, it's 50 times better of a leaving group because it's a large group, right? Can share the electron charge among a larger space. Iodide is an even larger one, so it can share the electron charge more, distribute it more, and so again, 150 times. And there's our tosylate, which is one of the best leaving groups right there. And so this is an SN2 reaction, okay? Remember that in an SN2 reaction, you have two things you're considering. Your attacker and your leaver, okay? So the attacker, the better attacker, is going to have, relieve the stress on that leaving group leaving, right? It's going to force off even things that don't leave very well. Okay? You get a good enough attacker, you can have hydroxide come on. Okay? But that's a really powerful nucleophile. That is really extreme. Okay? We go down to the SN1 reactions, and what we see here is that when you're talking about your leaving group, it becomes much more important. So your leaving group becomes incredibly important. And so here we have those same ones we were talking about. There's the chloride. Again, that's going to be your basis that everything is relative off of. Right here is going to be the bromide. It's only 10 times better now. See that? Right here, we actually have water. That's that H3O plus we were talking about. Let me know why that wasn't listed up here, by the way. So to get a decent nucleophile, they also have to be bases, don't they? Yeah. So if you have an extra proton on something, it can come off as the acid, and it would have neutralized our nucleophile. Okay. That's why you essentially never see H2O's leaving group where we have an SN2 reaction. Okay, it's very, very unusual. Okay. And so this will be a very good leaving group. Iodide is an even better one. There's the tosylate. And this is one of the best leaving groups to ever be made right here. TiO. Very, very fast leaving group. Yeah, extremely good. Yeah, it's a lot. 100 million, right? Times the speed. This is a very good source of carbocation if you ever need to make them. Okay, so this is the leaving group ability. So the relative leaving group abilities are going to be governed largely by the stabilities of your leaving groups in the form in which they come off the substrate. That's that same sort of rules we had talked about in Cardinal again. We're just looking at the stability of their product, right? Now, for an SN1 E1 reaction, remember your leaving group has to leave on its own. It's very sensitive to that leaving group ability, so the better your leaving group ability, the more likely it is an SN1 E1 reaction. The faster that reaction is going to go, and that's the only thing it depends on. Okay. For your SN2 E2, the leaving group assists the attacking species. It's not as sensitive to that leaving group's ability. Though remember that it still is half the equation, right? It's still part of the equation. Okay. And so the strength of your nucleophile, the strength of your attacker, the strength of your base is going to be one factor in the SN2s, E2s, and the ability of your leaving group to leave is going to be the other. Okay? But significantly less impactful in SN2 as E2. Okay, so these right here are going to be the leaving group abilities, just ranked in general. And so these are very good leaving groups right here. You can see your tosylates and stuff right there. Iodide is a very good leaving group. H2O or a alcohol as your leaving group is also very good. Remember that these would have been the protonated oxygens when you started. Okay. This right here, these are poor leaving groups. And these ones are just unsuitable leaving groups. They would be so powerful as bases or nucleophiles that they're just going to come right back and attack it again. Okay, so you're never going to see these as leaving groups. It would be very, very unusual to ever see these. Okay, now with a good leaving group, an SN2, SN1, E2, and E1 reactions are all feasible. Okay, you can have any of those. If you have a poor leaving group, then you really can't do an SN1 and E1. That's just not going to be in the cards. You just can't do it. You would spend weeks, months, maybe trying to get the reaction to have any product. Okay, so you'll never see it. So it's going to be an SN2 or E2 reaction if it's a poor. If we have an unsuitable leaving group, then realistically they're just all going to be unfeasible because your leaving group just is not going to leave. Okay, if you never get a leaving group, then you don't have any of those reactions. So if it's in the unsuitable list, you're just out of luck for any of it. Okay. Now, better leaving groups are going to tend to be weaker bases. That's the overall trend here. And so you may have noticed, again, the conjugate bases of strong acids tended to be your best leaving groups, right? even this looks like the conjugate base of like a sulfuric acid, doesn't it? Okay. And so notice again, that's still very similar to a conjugate base of a strong acid. Okay, so sulfonate anions as leaving groups. These make some of the best leaving groups that are available. And so they are very good leaving groups. They're going to be the conjugate bases of strong acids. So if you were to protonate these, they would be strong acids. Okay. Most of them you've never seen as acids, though, just because they would be so acidic, they would react with everything around them, and you wouldn't be able to have them in those polyps. But they do make acids, though. There's an entire series of strong acids you guys have never seen because they're too expensive to even bother using in an aqueous reaction. Okay. But if you start going in something that has a less solvent leveling effect, right, you can start seeing these. Okay. So again, they're going to be weak bases. They're going to be similar in structure to your conjugate base, which is the H2SO4. That would be the bisulfate anion. That's actually this one right here. That's the conjugate base to sulfuric acid. Okay. Now you can convert a poor leaving group into a good leaving group. Okay. So for example, OH minus was a very poor leaving group. It's unsuitable for most reactions. And so if you try doing this reaction under neutral conditions here with sodium bromide, this reaction's not going anywhere, right? We're not getting an E1. We're not getting an SN1 and SN2. We're just not getting anything, okay? And so we sit there for weeks and nothing happens, and life is unhappy, okay? But if we put this under acidic conditions, so we use HBr, well, what's the first step of that reaction then? Under acidic conditions, this is going to be the H2O plus, isn't it? Yeah. H2O is a good leaving group, isn't it? And so we've actually generated a good leaving group. And so we're going to start getting this substitution reaction here. And it'll give us 99% yield. And so that works excellent, doesn't it? This is actually your mechanism for your SN2 reaction of that alcohol under acidic conditions. And so you would actually have this attacking the hydrogen there, right? We have the protonation step, that proton transfer step, generates the bromide. The bromide's actually going to act as our attacker, isn't it? Okay. This is actually one of the few ways you can generate your attacker in an acidic solution. You have to have something like bromide or iodide. Chloride can also work with slower, typically. Okay. So we're going to get a bromide attacking the carbon then. This is going to have our H2O leaving group, leave, and that's our SN2 reaction, isn't it? And so we go ahead and get this. The Br minus and I minus here will almost always do the SN2 reactions. Okay? Because remember that they're better attackers. So again, this is the alcohols as leaving groups. Again, if we tried to just straight up attack an alcohol, it would come off as the OR minuses, right? Those are unsuitable leaving groups. And so if we do them under acidic conditions, we can actually get this reaction happening. It'll give us 72% yield over the course of about 7 hours. Okay. Don't forget, you don't have to be there the whole time. So you typically set up reactions and go do stuff. Go to classes, etc. if you're an organic chemist. Now, the mechanism for an SN2 reaction of an ether under acidic conditions is going to look like this. Again, we have the proton transfer step. We generate a better leaving group, and then we get the SN2 attack. Okay? And that will give us our product. Now, our proton transfer, this is going to be a proton transfer facilitated elimination reaction we're going to look at next. And so this is actually going to give you your elimination. Now, getting a good leaving group can also facilitate elimination reactions like a dehydration. And so, has anybody heard of dehydrations before? Maybe in biology? Yeah, dehydration is a very common reaction you would see in biology, actually. In fact, the same mechanism we're going to talk about, very common in biology. So this is a dehydration reaction. We're going to have a H2O coming off. It's going to leave us with a double bond. Okay? And so we're going to put it under acidic conditions here. Everybody see we have the acid there, right? And then we have 95 degrees, and this gives us 91% yield. So what we're doing here is we're putting the proton on in that proton transfer step, right? We're going to get our H2O leaving group, the H2O plus. In this case, we have a pretty poor attacker here. It's very stable in that resonance stabilized phosphates. And so what's going to end up happening is we're going to have heterolysis, and that's going to generate our carbocation. We have an aqueous solution, so we have water available that can act as our base. And this is actually going to deprotonate that hydrogen. And that's going to give us our electrophilic elimination there, which will give us our double bond. Notice we generate H3O plus at the end here, which is the acid. Do note that this is actually kind of interesting because we actually regenerate acid at the end. Now, this is actually an amine as a leaving group. So again, you can protonate an amine. That will make it a better leaving group as ammonia. This is actually in the form of an ammonium salt. And so it's kind of interesting because if you get ammonium salts, oftentimes they'll be set up for this reaction to occur already. Okay? So if you actually take a lot of different ammonium salts, you can actually just heat them and it'll do the reaction. Yeah. So it's kind of a bizarre thing. Do note that if you eliminate an ammonia, right, you can actually get this ammonia coming off as an H3. That's a gas. Okay? It'll be an irreversible reaction typically because you'll have the gas escape. Okay. So these amides right here, if you were to have these coming off, they're always going to be these basic groups. They're very basic. They're all going to be poor leaving groups. If we protonate these under acidic conditions, what we'll see is we'll typically actually form the ammonium salt first rather than the SN2 reaction. You need a lot of energy to go through to the SN2 reaction. Okay? So you'll actually get the salts typically rather than the SN2. Let's talk about hybridization. So hybridization, your SN2, SN1, E2, and E1 reactions generally do not occur unless the carbon atom bound to the leaving group is in sp3 hybridization. This is partly because your sp2 and sp hybridized carbons are going to form stronger sigma bonds than your sp3 hybridizations. That stronger bond is actually going to make it more difficult for your leaving group to leave. And so you would need actually a better leaving group than normal, and it just slows the reaction down in general. So this right here is going to be your SN1 and E1 reactions. They don't generally happen unless you're using an sp3 hybridized carbon there. If you have a double bond or a triple bond there, this is not generally going to happen. It's not generally going to have the leaving group leave because this is going to be an excessively unstable carbocation. Now again, theoretically, you would think that you could. It's just it generates an excessively unstable carbocation. And the reason for that has to do with the orbitals here. So your SN2 reaction is going to be further hindered in this case, and that's because of the electrostatic repulsion. So remember, when we're talking about a double or triple bond, right, they have pi bonds, right? So this is going to have this shell of electrons above and below. Okay. Now what that means is that a nucleophile coming in here and attacking this carbon is very, very difficult to achieve, right? We have a shell of electrons. The nucleophile has a negative charge. It has to come in and attack with, right? And so they're going to repel each other. Okay. And so again, your SN2 reactions on anything but an sp3 hybridization is very unlikely to occur if you have any sort of pi bond. So this right here is going to be the effects of alkyl groups on your rates of your SN2 reaction. So remember where we hindered our bases and we made them worse for SN2s? So instead of hindering your base, you're hindering your substrate. So we're crowding out that substrate. So instead of assigning the defenders to Michael Jordan, we're assigning them to the basket. And we're crowding out the basket. Okay? Okay. Everybody knows Michael Jordan is okay with Michael Jordan? Okay. All right. I guess Michael Jordan is my go-to now. He is the GOAT. All right. Now, relative SN2 reaction rates here, we would see like a methyl, for example, would be your fastest because your attacker has easy access to the carbon. There's only hydrogens blocking it, right? If we look at the next one, which is primary, this is going to slow it down considerably because we're blocking off part of our where we would attack, right? So you are blocking off part of that carbon. If we get a secondary, this is going to slow it down tremendously, and that's because we're blocking off all but one approach to that carbon. And so it has to make it into that one approach. Remember, molecules and atoms are not smart. They're not being guided by some intelligence, right? They're just randomly bouncing in there. So it'd be like having a basket where you've blocked off all but a little space. Like the chance of a random ball just bouncing in there is pretty small, right? And so if we have a tertiary, on the other hand, then we have to come in with so much energy, and it has to have that electrons actually reach in there, that becomes almost impossible. Okay? A tertiary blocks off essentially every approach of that carbon, right? And so your SN2 reactions become essentially impossible. Okay? They're going to be so slow that they're just not going to happen in a reasonable amount of time. See how fast that rate drops off, by the way. So the more crowding you have around there, the faster the rate drops off. Now, the rate of your SN2 and your steric hindrance, this is actually what that looks like. So you have here the methyl, you're being attacked, right? And you have free access to it. Essentially, you just have these little hydrogens blocking. They don't do much. So the methyl, again, this is going to take up space like that, right? It's a big area of space it actually would reject stuff. Remember, it has a slightly negative charge to it, okay? And so you'd have to attack from one of these other areas, right? This, we blocked off most of the space, secondary. In the tertiary, we've essentially blocked all the space. Technically, it can reach in between and get an attack sometimes, but the likelihood of it happening is incredibly low. Okay? It's very, very, very slow. Now let's talk about the alkyl rates on the SN1 reactions. So does anybody remember our carbocation stabilities? What was our least stable carbocation? Methyl, right? What was our next least stable? Yeah, where we have one carbon attached to it, primary, right? And so if we have a secondary, it was more stable, right? And then we have a tertiary, and carbocations actually start becoming relatively stable for a carbocation. And so it actually goes in the exact opposite way as an SN2. So the more alkylated that carbon is, the more likely it is to go an SN1 reaction. Okay? And this will actually greatly increase the speed of your SN1 reactions, having it more alkylated. Remember, in this case, where we have the SN1 happening, we don't have an attacker that needs to attack that spot. It being more crowded is just not an issue. When we have an attacker coming in, it's going to have a free p orbital on both sides, right? From the carbocation. And so again, this would be your carbocation right here. And so as we get more substituents on this carbocation, we have a greater inductive effect, and we can stabilize that carbocation, right? That's going to reduce your intermediate. That's going to reduce your transition state energies. And so your reaction goes faster and faster and faster. Okay. Note that even though I said SN1 up here, I believe, yes, it's the exact same first step for an SN1 and E1. Okay. So this methyl substrates is the exact same thing for SN1 E1s. There's no difference. Okay. Now, which substrate, A or B, undergoes an E1 reaction faster? Which one would be faster? Okay, so the two things you're looking at, leaving groups and methylation, right? Okay, so your leaving group right here, right? Which is the better leaving group? It's the same. So we're just looking at methylation, aren't we? Okay, which one has more methyls? B. Yep. And so that one's going to be the more substituted one. That one's going to have the more carbons. This one, in fact, is a tertiary right there. And so that's our faster one right there. It's the more stable carbocation. Now, your E2 reaction, these are going to have relatively insensitive to the number of alkyl groups on the carbon bond to the leaving group because you're not attacking that carbon. You're attacking the hydrogen next to it, right? And so the substrates with leaving groups on primary, secondary, tertiary carbons can usually undergo your E2 reactions quickly because, again, you're not attacking the carbon. You're attacking the hydrogen next to it. So it's more exposed. So this is actually your summary of the influence on these different reactions. Okay. So this right here is going to be the allyl cation and benzyl cations. Now this again is going to be a, don't get this confused with directly on the double bond. Okay. This is going to be adjacent to a double bond. Right? Adjacent to a pi system. So when you're adjacent to a pi system, what does that mean in terms of your carbocation? Well, they're more stable, weren't they? Okay. Remember, that was one of those stabilities. It was the same thing as like this was about the same as being a secondary carbocation, wasn't it? Okay, so being adjacent to the allyl system is actually going to stabilize your carbocation. It does one other thing though as well. And that's that you have resonance structures, right? And so what's going to happen is you actually generate a carbocation, a positive charge, on several places. And that's where your resonance structures puts that positive charge. Everybody see it okay? So yeah, this carbon's positive, sure. But remember that this is a combination of these structures, right? And so you actually have positive charge on both of those carbons right there. Okay. And what tells you that is this resonance structure. So you can get attack at both of these areas now. Okay. This one right here is off a benzyl group. And so again, if you make a carbocation off of a benzyl group, this is again going to have resonance structures, right? Where it's going to spread that positive charge throughout your ring. Okay. It's actually going to be here, here, and here, in case you're wondering. This has some really, really interesting properties, by the way. And so, like, one of these uses for like an allyl chloride is going to be manufacturing of like epoxy resins for protective coatings. And if you look at like the picture of the boat in your book, like that epoxy resin on your boats and stuff, that's what that is. It's allyl chloride usually. Okay, so yeah, very common like resin, excuse me, structure. Resonance. Now, which of the substrates A or B would undergo an SN1 reaction faster? So what we're looking for is what will stabilize that carbocation better. So if we make the carbocation right here, this is going to have that oxygen lone pair that can come into a double bond, right? And so it has a resonance structure. That's a delocalized electrons that can be brought into a double bond to give you a resonance structure. So it can share that positive charge a little bit. This one, on the other hand, just has no resonance stabilization possible. There's just no delocalized electrons to move around here. Okay, and so they're both secondary carbocations. There's no difference in that. And so A would end up being the faster one here because it has those lone pairs on the oxygen that can do the resonance structures. So let's go ahead and talk about the solvent effect here. The polar aprotic solvents are going to typically favor the SN2 and E2 reactions. On the other hand, the polar protic solvents are going to favor the SN1 and E1 reactions. So this right here is going to be your anion. Here we have a protic solvent. We have those hydrogens, right, that can do like a hydrogen bonding interaction with our anion. And so we can strongly stabilize these. If we have an aprotic solvent, that means that does not have a positively charged hydrogen on there, does not have that little hydrogen bonded to an oxygen, nitrogen, and fluorine usually. This is going to stabilize our anions like this. Notice it's going to be weakly solvated, and it's not very heavily stabilized. Okay. All right. We'll start up here next time. You all have a wonderful day. And the exam is coming up, though not this week. Next week, Tuesday, right? Okay. Everybody take care. Have a wonderful time. I'll see you Thursday and Friday. Many of you, probably more than you may have wanted.